Yeah, thanks a lot, Marcus. Okay, so yesterday we talked about basic cosmology, something about neutrino physics, neutrino decoupling, for example. Then I went on to start the discussion of how one can actually probe neutrino physics using cosmology in a little bit more quantitative sense. And the first place we're looking is Big Bang nucleosynthesis. And this is the outcome of a typical BBN calculation. This is more or less where we ended yesterday, right? So most of the neutrons that are available in the universe end up in helium-4 because it's the most tightly bound light nucleus. There's a small logarithmic dependence on the baryon abundance as to how much helium you get in the end. It's not very strong, which means that it's actually quite tricky to measure helium and infer the baryon abundance. Deuterium has a much more steep dependence. On the other hand, as it turns out, it's also much more difficult to measure deuterium, mainly because it's an isotope of hydrogen. And therefore, when you try to measure deuterium, you always measure hydrogen first. And you typically see deuterium only via small isotope shift, as we'll see in a moment. Okay, so helium-4, that was why. It depends on the baryon abundance. Let's move on. And this is more or less where I ended, right? That was measuring the helium-4 abundance. And as I said yesterday, that is typically done in what we call metal poor systems. And metal poor just means pristine, unevolved matter in the sense that it hasn't been through stellar evolution at any time. So solar material, for example, has a helium abundance of something like 28%, whereas we know that we should be looking for something which has a helium abundance of more like 0.25 or thereabouts. And those systems you can actually find. They're typically these ionized hydrogen systems in the small or large Magellanic Clouds because they are much more metal poor than the Milky Way. Here you see some of the measurements. And this, I think, was the sociology lesson of yesterday, at least in my lecture. So this was the measured or inferred helium abundance as a function of the year where the work was done. And we saw this very nice separation into two peaks corresponding to two different groups getting vastly different results. And mind you, these are the same systems that are being measured. So these are exactly the same astrophysical systems. It's just that various assumptions, of course, have to be made typically when you do these astro observations. And those assumptions were different. And only when we had access to CMB measurements of the baryon abundance was it actually realized, as it should have been all along, that the systematic errors are probably much, much, much larger than people liked to think. And I remember actually being at a PhD school in Trento in Italy in 98, thereabouts, and people were seriously discussing measuring this third digit out here, right? So 0.24, 5, or 6, that was seriously discussed. Of course, that's all rubbish, basically. It cannot be done from these systems because there's so much systematics going on. Okay, deuterium is even worse. Deuterium can be measured astrophysically in a variety of contexts. It can be measured, for example, in meteorites. So what we can say is that the solar system value has a certain level of about a little more than 10 to the minus 5. And deuterium has the problem that it's very lightly bound or loosely bound, and that means that it's typically destroyed in astrophysical systems. So you can take this as sort of a lower bound rather than an upper bound on the primordial value. And close to 30 years ago now, people realized that it's actually possible to measure, or should be possible to measure deuterium in high redshift absorption systems. So this is like a typical quasar spectrum here. You have a big, big, big Lyman alpha emission line sitting at a high redshift here. And then we have the what is known as the Lyman alpha forest in between us and this emitter. And these are just hydrogen absorption clouds, so neutral hydrogen, basically. And if you zoom in on one of these saturated Lyman alpha lines, you see a small side lobe here, which can be interpreted as deuterium. However, it could also, and perhaps equally well, just be another hydrogen cloud at a slightly different redshift or a slightly different velocity, and that can be extremely hard to distinguish between. And therefore, these measurements are inherently very hard. And as you can see, when these results first came out, there was something like an order of magnitude difference between different groups. So these results came out first. They indicated that the high redshift value was about an order of magnitude higher than the solar system value. And people were super interested because that implied that we had very, very non-standard BBN going on. But then a little more than a year later, we had other measurements which were much closer to the actual prediction of standard BBN. And as it turns out, this is more in line with the correct value that we know now. Many of these systems have been measured. The consensus is that deuterium has an abundance of something like 3 × 10⁻⁵, completely consistent with standard BBN. So nothing funny going on as far as we can tell whatsoever. So if you put everything together, you can get these likelihood posteriors for the various abundances. And you see the inferred baryon abundance from this. You see that deuterium and helium-4 are consistent. We also see that lithium-7 is low. We don't know why that's the case on purpose. I won't discuss it because that's even more complex and the status really is up in the air, so to speak. It might be, I wouldn't bet any real money on it. It might be because we have some non-standard BBN going on. We could have massive decaying particles during BBN that can typically also the lithium abundance if it happens sufficiently late without altering the other abundances. But much more likely, it's just that we really don't know what happens to lithium-7 between BBN and now. It can both be destroyed and created in various settings, and therefore interpreting a measured lithium abundance in terms of a primordial value is really difficult and probably next to impossible. What we can say is that if we disregard lithium, then everything is also consistent with the CMB inferred baryon abundance, which is about 6 × 10⁻⁻10. So that sits roughly here, more or less on top of the other curves. So at least when you look at this data, everything is consistent with the standard model picture. And that means that the best we can hope for in that sense is to put constraints on non-standard models using this type of data. So if we turn back to neutrinos, how do they affect BBN? Well, they affect BBN, for example, via their effect on the expansion rate of the universe. So remember that the weak decoupling was calculated, or order of magnitude of the decoupling could be calculated by comparing the interaction rate with the Hubble expansion rate. Now, if you just add energy density to the universe around BBN without specifically altering particles that go into the weak interaction, meaning electron-type neutrinos, then what you do is you fiddle around with the Hubble parameter, because you essentially alter this capital N parameter. You have more degrees of freedom, therefore you have more energy density, therefore you have a higher Hubble parameter at any given point in the temperature evolution of the universe. So you have a faster expansion rate. That means that everything decouples earlier than it would have done otherwise. So that's one way that additional light species like neutrinos alter BBN. So for example, they will lead to a different amount of neutrons available. The weak interaction decouples earlier, so you typically have more neutrons around. And therefore, what you can see here is that there are curves. So this is the logarithmic dependence curve of the helium abundance on the baryon density. And these are 3 different curves, one for 2 neutrinos, 3 and 4 neutrinos. And of course, this is wildly exaggerated in the sense that we probably don't have an extra neutrino degree of freedom floating around, but this is just an illustration that you actually get quite significant changes, and therefore BBN can be used as a probe of non-standard physics, in the sense that it can probe light degrees of freedom that are around. It's a very poor probe typically of dark matter, of course, because dark matter has no dynamical influence on the universe at these early times, unless it's a very non-standard type of dark matter. And therefore, this is mainly related to what you would call dark radiation. And this is a typical posterior that you would get as a function of the baryon density and the number of neutrino species. And it's a little bit old, so actually it should be shifted a little bit downwards, but it's more or less correct. So this is typically what you can get. I should also say that apart from testing the expansion rate during BBN, of course, you also, in principle, can the interaction rates. Well, first and foremost, of course, they enter into each other. So if you had more of these neutrinos, then you would shift the decoupling time. However, okay, so if you go back 20 years or so, people used this quite a lot as a way of probing, for example, a neutrino chemical potential, stuff like that. However, once it was realized that neutrinos do oscillate quite rapidly, and the large mixing angle solution is the correct solution to the solar neutrino problem, it was realized that there's basically complete flavor equilibration in the early universe. And therefore, you cannot, have many tau neutrinos floating around while having few electron neutrinos. You change all neutrinos at the same time, and that leaves extremely little room to wiggle around, because as soon as you change the abundance of electron neutrinos, you change the weak interaction rates, and that radically changes the outcome of BBN. And therefore, that field essentially died out. It was closed, more or less. We know that standard modern neutrinos have standard Fermi-Dirac distributions to a very good precision from this. And we know that there can be at most of order what corresponds to 1 extra neutrino degree of freedom during BBN in terms of light degrees of freedom. So that could be light axions, it could be myrons, it could be any other type of almost massless degree of freedom. And by almost massless, I just mean significantly lighter than the keV scale. It doesn't have to be light compared to what the temperature of the universe is today. It just has to be light compared to any of the processes that we're looking at here. And I think that was it. Now I'm done with yesterday. So and let's move on to today. Can you do that?
Maybe if there's a question.
Yeah, we can also. Yeah, absolutely.
I suppose this is more of a question about the field in general. So you've shown us a lot of things and measurements from like 20 years ago. Is there anyone are people still actively working on this today, or is this more of a review thing?
Well, some people, it's a small field, I would say. And unfortunately, not much has happened really in the field of BBN. And I think it's just that after this realization that systematics are typically quite large, and the onset of CMB measurements, people lost interest, basically. So it used to be the main probe of the standard model of cosmology up until the 90s. And then it sort of died out for the very simple reason that CMB is so much more precise and has so much less systematics involved. But one thing that one should keep in mind is that BBN is still relevant in some contexts. And there are some beyond standard physics models that can be tested using BBN, but would not be testable using CMB, simply for the reason that they occur at vastly different temperature scales. So the CMB is something that takes place, as we'll see today, at a temperature of a fraction of an electron volt, whereas BBN is at the keV to MeV scales. That's okay. It's not my laptop, so I'm very relaxed. Any other questions? Yep.
I was wondering about this eta parameter. It's the photon to baryon ratio, right?
Yes.
But it's not constant, right? Photons are created all the time, but baryons are not destroyed all the time.
That's true. If you okay, so first, of course, if we go back to what I talked about yesterday, we know that when electrons and positrons annihilate, they dump the entropy into photons. That changes the baryon to photon ratio. So even during BBN, it's not a constant. So what do we mean by eta? So what I mean by eta is the way it's normally defined, it's just the baryon to photon ratio after BBN is done. Then you might worry, as you say, that, but lots of photons are created in the universe. We could say, okay, let's disregard those and just take this microwave background radiation. But if you actually count the amount of energy that's in all emitted photons from the entire lifetime of the universe, that's minuscule compared to what is in the CMB. Put another way, the amount of entropy production during the lifetime of the universe after BBN is completely negligible. It's a super, super good approximation, just an adiabatic evolution. There's no entropy created. And the photons that astronomers are interested in make up very, very little, really.
Okay, so eta 10 or eta is more or less constant.
After BBN, it's very, very good approximation, just constant, yes. Contrary to what you might intuitively expect, yes.
Okay, thanks.
Yep.
Good.
Are we good to go? Oh, excellent. Okay, so that brings us, well, basically to today's lecture, but also much further on in time research-wise. Because like I said just before, BBN was really in some sense the first central pillar of modern cosmology, and there was where all non-standard models could be tested. And the simple reason that was the case was that we had very little information about structure in the universe. We had very little information about the CMB. Then in '92, we had the first measurements from the COBE satellites on the CMB anisotropy, which was nice. But quickly, people also realized that a much more precise measurement of the CMB anisotropy would allow you to actually extract all kinds of parameters about cosmology, including neutrinos and other stuff. And the same is true for large-scale structure. And in order to understand why that's the case, I think it would be good to go through the basics of structure formation. And some of you might know this very well already, so just fall asleep or look at TikTok or whatever. But I think to some people, this will be relatively new. So what we start from, and what I'll stick with more or less, is that we relax the assumption of homogeneity in isotropy that we had up to this point, but not very much, meaning that we allow for small density perturbations, but not radical perturbations in the sense that we are not interested in forming a galaxy, for example. We're interested in structure on very, very large scales, which is always in what we call the linear regime, meaning that in real space density, contrasts are small compared to the average density. So that's the underlying assumption that we'll have throughout the day, more or less. So if you go back to classical fluid mechanics, so this is what you would see more or less in many types of physics courses. Since we have gravity involved, it would typically be in stellar astrophysics. So if you wanted to look at how do I form a star or a planet or something like this from some protostellar cloud, these are the equations that you would use. So these are just basically conservation equations, the first two, right? Continuity equation is the energy conservation equation in another form. And the Euler equation is the momentum conservation equation. And these are simplified fluid equations. Some of you who are familiar with fluid dynamics will know that the Euler equation is not, okay, so no more pointer here. Okay, let's. I really couldn't care less. Oops. Okay, whatever. I can use my hands. Okay, so the point is the Euler equation is not the fundamental equation. That's the Navier-Stokes equation, which has an additional term which corresponds to any entropy generation. That will become important in a little while, but for now, let's stick with what I said just before. To a very good approximation, this is an entropy conserving environment that we're interested in, and therefore we throw away everything that generates entropy and just look at perfect fluids. And in that case, we have a closed system of equations. Here we have the two conservation equations plus the field theory, field equation of gravity. Help, Marcus. No pointer.
It's sometimes hiding a little bit. Sorry.
Ah, excellent. Okay, we're good to go again. Okay, thank you. So this is just a very completely classical system, which would apply to, for example, a protostellar cloud. Now, if we massage this a little bit, then let's see, I think, yeah, this is where we started from. Okay, let me just point out that what we do is we make a perturbative expansion. So we have a homogeneous background, which is assumed to be at rest, and then we perturb it, and then we write out the equations for the perturbed quantities, which look like this. Now, if you differentiate this with respect to time, and you insert this cross term from the Euler equation, then we can get a wave equation, a normal second order wave equation that looks quite familiar in the sense that if I put my hand over this, this would just be the equation for a sound wave or a pressure wave propagating in a gas with the sound speed given by Vs and nothing more. The only new thing is that now I have the appearance of a great gravitational source term, which could alter the solution quite radically, actually. So the solution, of course, is still, as it must be, an exponential that looks something like this. However, the dispersion relation is completely different, potentially, from what we see in a normal pressure wave, in the sense that omega squared equals Vs squared k squared. That's the standard result, right? But now we have an additional term with opposite sign. And that actually means that depending on the magnitude of the source term here, compared to the pressure term, which is this one here, you can actually flip the sign here. And if you have a negative sign of omega squared, that actually means that you would have an exponentially growing solution because you have real solutions up here all of a sudden. So that indicates the onset of gravitational instability in the system. And you can also sort of intuitively understand how this comes about, right? So if we think about the pressure term, that has a k squared. So think of that as the Fourier wave number. So a large k corresponds to a small physical scale, and a small k to a large physical scale. It's just the wavelength of the wave, or rather the wave number of the wave. Now, if you're on very small scales, this becomes very large, and that means that the sign is always positive. And that's not surprising, because pressure, in the sense of producing a force term from a pressure gradient, is always a local effect, whereas gravity is a long-range effect. And therefore, on small scales, pressure always wins. And on large scales, eventually gravity will win. The scale at which that happens depends on the mass of the object and the sound speed. The higher the sound speed, the more gravity, of course, you need to collapse this thing. And we can condense that into this Jeans wave number, which basically indicates where the onset of instability occurs. So that's completely standard up to this point. If you take a course in star formation, for example, these are some of the first equations that you will encounter. But of course, they don't apply to our actual universe in the sense that this was a static background, for example. That's one thing that we should remedy. So let's stick with the Newtonian world. For now, we have no relativity whatsoever in any way, neither special nor general relativity. But let's see how far this Newtonian approximation actually gets us. So the next thing we could do to remedy the situation is to have an expanding background. So let's assume that we have a density, background density, that scales as 1 over a cubed. That's just normal non-relativistic matter, right? We know the energy density. goes as 1 over volume. If you have a fixed number of particles and you expand the box, that's what you expect. Then we have a background velocity field, and that background velocity field should obey Hubble's law. So that should be basically what you're getting from the Friedmann equation. So we can put that in by hand and just say that, okay, let's assume that the unperturbed velocity field goes something like this. And you would also get, and mind you, of course, we're cheating big time here, right? I mean, these are Newtonian equations. In no way should they apply to cosmology in general, but let's see how far we get from it. And some of the tricks will be reused later when we do the GR version of it. So these are the perturbed equations. They look more or less the same as before, except that now we have the appearance of some new terms that are related to the expansion of the background. So we have all these A dot divided by A terms. And then we could, just to simplify life for ourselves, do an additional trick and just convert everything to Fourier space. And this, as it turns out, is what we always do in cosmological perturbation theory, convert everything to Fourier space. And the reason for it is that if you look at this, it's a set of partial differential equations. We have spatial derivatives and we have time derivatives. However, if we converted everything to Fourier space, and instead of looking at these quantities in real space, look at the Fourier quantities, it's fairly quick to realize that all spatial gradients become algebraic multiplicatives, in the sense that a gradient operator, if you do it on the Fourier component here, drags down a minus ik, and then it's just multiplied with. And that life becomes so much simpler in the sense that you reduce this to a set of ordinary differential equations rather than partial differential equations. It makes it much, much simpler to work with. And that trick will also be used when we do the GR version of the same equations. So the wave equation that we had before now, of course, doesn't have an Laplace squared operator. Rather, it has a k squared here. So already when you look at the equation, there's no gradient here. So what you can see is it's essentially the same equation as before, except for the appearance of a new term here. And then we have to scale this quantity with a squared. But other than that, it's the same thing. Now it's just the equation for delta k, which is the Fourier component of the delta field. So the question is, what does this do? This A dot divided by A term. If you looked at this in a normal oscillator equation or a wave equation, you would think, but that's a friction term, right? It's something proportional. The sign of it, if you flip it to the right-hand side, becomes a minus, and the magnitude becomes proportional to velocity. So it's a typical friction-like term. And intuitively, what it should be doing is that instead of, say, you have an exponentially growing solution, it must break that solution, right? It must become much more moderate in its growth rate if you have this friction term. So that's intuitively what should happen. And of course, in reality, it's also indeed what happens. This friction term turns out to be extremely crucial. And it just comes from, as you can see, A dot divided by A. So it's just the Hubble parameter. It just comes from the expansion of the universe. So the faster the universe expands, the more difficult it is for stuff to cluster. Not very surprising, right? I mean, it's what you would expect. So let's see what comes out. Now, if we take the simplest model, just the flat matter-dominated model. So go back to what we talked about yesterday, where we have a universe that has radiation and matter and dark energy and whatever else, and just say, okay, let's assume everything is in matter. And then we plug in what is the Hubble parameter, how does the scale factor behave with time, then we reduce it to this differential equation instead. And you can try and solve it for yourself. What you find is, of course, it's a second order equation. There are two linearly independent solutions. One is a growing mode, but it doesn't grow exponentially fast. And the other one is a decaying mode. So that means that rather than having exponentially growing solutions, we have very slow power law growth. And then another question, of course, is what happened to the sound speed term here? Any guesses as to that? What have I assumed here, do you think? Any guesses? So if we have a completely matter-dominated universe, I think we talked about it yesterday, and we talked about pressure. So what was it that we assumed for the pressure of dark matter, or baryons for that matter, in this context? Do you remember? It's just zero. Big fat round zero. So it's assumed to have no pressure, and no pressure equates no sound speed. So this should be a system that is always exponentially unstable at any scale. And now, rather than exponential, it's just power law unstable. And that means that growth is relatively modest. As it turns out, if you have, for example, a dark energy dominated universe, what you find is that there are no growing modes. The mode that was growing before actually now becomes frozen so that the growth stops. Same would be true in a curvature dominated universe. And the same actually also is true in a radiation dominated universe. And that means that if we look at structure formation, so this was the matter dominated model, right? Where you just have this t to the 2/3, and then you add a cosmological constant. What you see is that you switch away from this growing mode, and then you enter this frozen mode. So qualitatively, let's just sum up what we've learned from this. And what might, we don't know that yet, but what might carry over to general relativity also is that in a radiation-dominated universe, you cannot form structure. In a matter-dominated universe, yes, you can form structure. It proceeds relatively slowly, and then it switches off again once the universe becomes dark energy dominated. And that means we have, so to speak, about 3 orders of magnitude in scale factor, where we need to form all the structure that we see in the universe today. It starts after matter radiation equality, and it stops before today. So structure formation is stopped at the current epoch. Of course, this is true only in perturbation theory, right? So this is not claiming that, you know, the Milky Way and Andromeda, they of course can still evolve because they are bound by the local mutual interaction rather than the global Hubble field, because we're far away from linear perturbation theory. But we will not see any further linear growth of the universe, which means that the largest structures that we see in the universe today, the superclusters, are the largest bound structures there will ever be in the universe. Even if we go 100 billion years into the future, that's still the case. Okay, so that's more or less what we could learn from the Newtonian approximation. Of course, there are many, many, many things that we were not able to do in Newtonian theory. Of course, boundary conditions, for example, are completely crap here, right? We have no way of treating them properly. And some of you might know that I've cheated big time when I wrote out the equations, because actually, even if we just go back to the very, very, very basic equation here, when I expand this, there should be a rho naught plus rho 1 term here. That rho naught term actually should have survived into this equation and acted as a source term also for the perturbation, which of course would lead to completely crazy results. And therefore, you typically just throw it away as a boundary term. However, formally, you're not really allowed to do this. So that's called the gene swindle. And in GR, as it turns out, that's never a problem because you can actually set proper boundary conditions. I mean, okay, so just sticking with this gene swindle for a moment. I mean, we know the problem in the sense that some of you, if you had a cosmology course, a basic one, you might have seen this tentative derivation of the Friedmann equation from Newtonian physics, where you just have a big ball of matter and you calculate the surface gravity on the surface of this ball, and you find that the equation of motion for this test particle actually corresponds to the Friedmann equation. But of course, that's completely bogus in the sense that if you have a homogeneous and isotropic universe, where do you put the ball, right? And we know from Newton's theorem that if you have a spherically symmetric distribution, all the matter surrounding wherever I'm sitting should not influence the local gravity. But that's only true for a finite distribution, not for an infinite distribution. Because for an infinite distribution, I can have no direction of the force vector, right? So we're led to a paradox in the Newtonian world if we go along this way. So that hopefully should not be the case in GR, and indeed is not the case in GR. So let's turn ourselves there. So how do you do perturbation theory in general relativity? Well, sticking with sort of the simplest possible thing, at least what we need is a metric, just like we needed the Friedman-Robertson-Walker metric yesterday for the homogeneous and isotropic universe. Now we need some other metric that is close to the Friedman-Robertson-Walker metric, but not identical to it. And you need to start writing out all the possible degrees of freedom that we have in such a perturbed metric. And as it turns out, there are 2 degrees of freedom related to what you could call normal density perturbations. Some of you, if you're familiar with GR, you will have seen this presumably in the weak field metric of general relativity. If you write out the weak field metric, there's this one additional term appearing, which is typically called phi, and which you can identify with the local Newtonian potential. So that appears both in the spatial part and in the time-like part of the metric. And there's exactly one scalar which corresponds to this gravitational field. Actually, it turns out that in the general case, there are 2 potentials, because the phi in the time-like component is not identical to whatever you call theta or something else that you have in the spatial component. These 2 are not identical. They are identical in normal weak field gravity, but in cosmology, it's not the case, because as soon as you have radiation, which has a non-zero quadrupole anisotropy, they become different. And that's really, really crucial if you look at the CMB formation, for example. Okay, so we have 2 linearly independent quantities needed to describe a density perturbation. Then, of course, we also have velocity perturbations, possibly. And we have gravitational waves propagating in the system. So all in all, we have more degrees of freedom. So here I just stick with 2. So these are just density perturbations, and we leave the other stuff for a dedicated course on perturbation theory. So another thing you need to worry about when you do this perturbation theory is that you need to pick a gauge that you work in. And this particular gauge is called synchronous gauge, the one that I've written here. And it's called synchronous because you see the time-like component is undisturbed by perturbations. So that basically means that we're working in a gauge in which all observers at rest measure the same flow of time. So immediately you know that that's not equivalent to the gauge that you normally write weak fields GR in, right? Because we know there's a term entering the time component. We know that the flow of time is different for different observers. And that's not the case here. So flow of time is identical for all observers. And of course, it's just one particular choice of gauge, right? So it's certainly allowed, but that means we have to put both of our perturbation components in the spatial part of the metric, and we typically call them H, I, J. But mind you, there are only 2 real components in there. Even though it looks like a 3x3 matrix. There are only 2 actual components in there. Okay. Yes, let's see. Yeah, okay, so that was the metric. And I'm skipping, of course, a lot of steps here. But once you have the metric, you take the Einstein equation, you write it out to first order in perturbation theory. Or you take the stress energy conservation equation, which is really just energy and momentum conservation. You write that out to first order. And then you get the continuity equation here and the Euler equation here. And I've thrown away a variety. These are still sort of semi-Newtonian equations. This is just to illustrate that even if we do this, we're still in trouble with neutrinos. And the trouble with neutrinos is that they are fast moving. They don't have 0 pressure. So they are fast moving particles until quite late in the universe. However, photons are too, of course. But more worryingly, neutrinos are non-interacting particles. And if you think about a fluid, so let's go back to normal fluid dynamics for a moment, and let's think about it could be a relativistic gas of particles. But if I have a fluid with a well-defined temperature and so on, I'm doing an assumption in the sense that I'm using an ideal gas. And an ideal gas requires fast interactions that can at all times equilibrate the system to whatever local temperature the system should have. So that would be true for the baryon photon plasma, for example. And for a perfect fluid, we know that's adiabatic. We know there are no entropy generating terms. And that means that we have only the continuity and the Euler equation. However, neutrinos are different. Neutrinos decouple, as we saw yesterday, at a temperature of an MeV, so way back in the early universe. And they are still fast moving. They still have a lot of pressure. But they also have, and that's the nasty part, they have what is called anisotropic stress. So they have components in the stress energy tensor that are non-diagonal and which you need to account for. And if you write out the equations here, what you would get is you get a term, which you typically call sigma. But that means this system of equations is no longer closed. You need an additional equation for this. And when you write out that equation, it turns out it has a source term in the form of a rank 3 tensor here, which you then need an equation for, and so on ad infinitum, right? So it means that this system of equations cannot be solved. Then you might argue, okay, but why is that not a problem for dark matter? Dark matter, after all, is non-interacting also. Why doesn't it happen for dark matter that we have all these problems? And the answer is that what you're actually doing here, if you start from a fundamental Boltzmann equation point of view, is you write out moments of the Boltzmann equation. You might remember from yesterday, the way we wrote out this collisional Boltzmann equation, it turned out to be an n dot plus blah, blah equation. That's actually the continuity equation. So that's just the first moment. Then you get a second equation here. If you take the Boltzmann equation, you multiply it by velocity. You do the integral over momentum space. You get the Euler equation, or rather you get the Navier-Stokes equation out. Okay, Navier-Stokes equation is not a closed equation. How do you solve that? Well, you go one moment higher. You multiply by VI, Vj, and you do the integral. You get this equation. Still not closed. You go one order higher, one order higher, one order higher, until you build this infinite hierarchy. And you can show that infinite hierarchy actually is exactly equivalent to the original Boltzmann equation, which, of course, again, remember, the original Boltzmann equation is an equation both in momentum space and real space. So that's a 6 plus 1 dimensional system. These are real space equations, so they are 3 plus 1 dimensional. So you get rid of 3 dimensions from integration, but the price you pay is you get an infinite hierarchy of equations. And that means, well, is that better? And in the sense of dark matter, yes, it's way better. And the reason it's way better is that the velocity of dark matter is very small. That means that every time I go up a moment, I multiply with a ridiculously small number, which is the velocity. And that means this is already small compared to this. This is very, very, very small. And to a very good approximation, I can just kill off this term, even if dark matter is non-interacting. The problem is that for neutrinos, that's a no-no. I can't do that because neutrinos are fast-moving. So I have to stick with this nasty equation here. So what we do is, like I said, indeed, we start from the full Boltzmann equation for neutrinos. And I won't go through the details, but I'll just try and sketch it so that you can sort of appreciate the steps that you need to take in order to actually calculate how neutrinos influence structure formation. So you write out a first order perturbation of the Boltzmann equation. And then, for example, you could do these fluid moments here, like I just said. And we can go, we can do that with the Boltzmann equation, right? So the prescription, if you start from scratch, is, okay, you choose a gauge, synchronous gauge. We could also choose what is called conformal Newtonian gauge, which is the one that you normally see in weak field GR. Then we write out all the equations in Fourier space. Now for this perturbed part of the distribution function here, which doesn't live in real space, but lives in Fourier space and momentum space, then we can expand it, for example, in Legendre polynomials, and we can get rid of parts of it. And the reason is that, okay, so this is dependent on the full vector here, K. But the point is that the universe is statistically rotationally invariant, right? So we cannot have statistically, at least, preferred directions in the universe. And therefore, we can get rid of directions. And we're left to think of it as, expanding the wave function of hydrogen, right, in YLM functions and the radial function. And the point is that if you think of these YLM functions, we have an orientation part which is given by the M quantum number. And then we have, if you go around a circle, the number of nodes that we have is controlled by the L quantum number. So that basically tells you something about the scale that you're looking at, but not the orientation. In the end, you find a set of hierarchy equations that becomes infinite. So this is corresponding to the continuity equation, the Euler equation, and the equation for anisotropic stress. And then you see there's a psi3 term appearing. I should go on here. And in practice, this, of course, cannot be solved analytically, so it has to be solved numerically. And there are codes available that do this. They started out way back when I was very young with a code called Cosmix. Then that evolved into a code called CMB Fast. Then CMB Fast evolved into a code called CAMP. And now there's the main code that people are using is called Class. So that's a code designed to solve the system of equations, typically going up to L of 2500 or so in principle. You can go very, very high if you want. Another thing that you need to worry about with massive neutrinos is that they are neither radiation nor matter. And that means that we actually have to keep, and I don't think I said that before, but you actually have to keep the momentum here, the magnitude of momentum, which means that if you solve it numerically, you do it typically on a grid in momentum space. So you have this big L hierarchy, and then you have a grid in momentum space that you need to solve. Okay, let's see. Yep. Okay, for dark matter, it's much simpler. Like I said, dark matter switches off either at order 1 or order 2, depending on the gauge you're working in. So dark matter is super simple. Neutrinos are very, very nasty. Yes. Okay. Yes. So what if you actually solve the system of equations? What do you learn? Well, what you do learn is that neutrinos really don't like to cluster. So if you actually plug in, if you actually solve this system and you find the solution, then you will find that it's a rapidly decaying solution. And the reason intuitively is that neutrinos are so light, and that means they don't like to cluster. There's nothing to drag them into potential wells. They have so much kinetic energy. And you can sort of, you can find out very simply up to what scales neutrinos don't like to cluster. So if you have a neutrino, it decouples at an MeV scale, but it has a mass of a fraction of an electron volt. That means for a very long time, it just basically moves at the speed of light. And how far does it move? Well, it basically moves as far as photons until these neutrinos become non-relativistic. And that means that the path it moves is comparable to the Hubble horizon at the given time. And that means that for neutrinos, any scale inside the Hubble volume is not a growing solution, it's a decaying solution. On scales outside the Hubble horizon, it's different. Neutrinos act like other types of matter. But inside the horizon, neutrino structures simply cannot grow. And that has a huge impact on structure formation. And if you go back to the 80s, or even before, of course, neutrinos, as some of you probably know, neutrinos were the main dark matter candidates because they are known to exist. And like I said yesterday, we had no clue what the mass of neutrinos were, right? So for all we knew, they could be the dark matter. If they had a mass of 30 electron volts or so, they would be very nice dark matter candidates, it was thought. But then you do this calculation, and then you realize it just does not work because neutrinos don't cluster. And they would produce a universe which is very, very far away from the universe that we are actually seeing. And therefore, cold dark matter was invented in the mid-80s. Okay, so before I show you observations, let's just spend the last minutes here today talking about how you actually quantify observations, because what I talked about so far have been basically just solving differential equations, right? So given, if I give you some initial perturbation field of the universe generated by whoever knows what means, inflation, presumably, then you would, if you follow these steps, know how to evolve that density field forwards in time. But how do you actually measure, how do you compare that to observations? Now, of course, we know that the universe is more or less homogeneous and isotropic. So we're probably interested only in the perturbation part. And the average of the perturbation, of course, must be zero if you average over a large volume. But the variance is non-zero. So that's the first thing that we could go for. So we would measure correlation functions typically, something like this. And since we're working in Fourier space, we would convert that and we would get these delta squared terms here. So that's the 2-point correlator in Fourier space, which is also what is typically called the power spectrum. So if you see a plot of structure formation in a condensed form, what you're typically seeing is a plot of this quantity here, which of course is not what is actually measured, but that is what is easiest to calculate from a theory point of view. So if you're a theorist, that's what you like to see because you know what to do with it. If you see something that lives in real space, that's much more worrisome because then you need to think. Okay, so yeah, we don't need to go into too much detail about this. This was what I said before. This power spectrum, of course, is the solution essentially to the equations that I just shown you. It's a squared quantity, but you also have to multiply with the initial condition that you get presumably from inflation. But it's an unknown quantity that you also have to measure. And this is actually where the problems of cosmology in some sense starts to show up, right? Because there's so many parameters that we need to measure simultaneously. Because when I go out and measure a power spectrum, it's a composite of all kinds of weird effects, not just neutrino physics or dark matter physics, but inflationary physics, baryonic physics, all kinds of things. Okay. Yeah, that's the initial condition. Typically, and I won't go into details, but typically from inflation models that are related to slowly rolling scalar fields, you would expect to get an initial condition that basically goes as k to the power n, where n is of order 1. And that is the generic prediction of most slow roll inflationary models. This normalization constant is not directly given by the theory. In a given theory, it is given, so to speak, but you cannot go out and measure it and relate this constant to the underlying theory immediately. It's more involved than that. Okay, so let's see. Yeah. So how do you measure this power spectrum? Well, you do, for example, galaxy surveys. There are many ways to do it, but galaxy surveys is one way. So this is what you see in a typical galaxy survey. This is from the 2DF. It's an old galaxy survey, but I think the figure is quite nice in the sense that, okay, you imagine you sit in here, then we measure the density fields. So every time you see a point of light, you set a dot, you measure the redshift of it, and you measure the position on the sky. That gives you a three-dimensional map in redshift. Of course, there are many problems related to doing something like this, and some of you might be familiar with some or all of them, but probably you're not all familiar with it. So if you measure a galaxy, what you can measure is its redshift. But the redshifts in a homogeneous and isotropic universe, the redshift gives you a one-to-one correspondence to the actual position of that galaxy. But in a non-homogeneous universe, that's not the case, because there are two effects, right? So one is that there's a Hubble distance, but the galaxy or whatever you're measuring might also be moving, of course, because it sits in a local structure of some kind. And therefore, this inference of distance from redshift becomes a little bit blurred. And the more matter you have around, the more difficult that becomes. Another thing which is equally worrying is that what we're measuring here are points of light. But points of light, that's not the same as mass, right? So what I've shown you on all the slides before, that would have to do with the matter power spectrum, the density power spectrum, not the light power spectrum, which is what we're measuring here. So you need to make sure that all your little points of light actually correspond to underlying matter. And there are several problems with this. So for example, galaxies can be measured only down to some limiting luminosity or up to some limiting magnitude. Otherwise, they become too faint. So it looks, for example, from this plot, like there are fewer galaxies out here, which of course is not true. It's just that the sensitivity of the instrument dies out here. But since we're measuring a density field, that's problematic in the sense that if there are fewer galaxies out here, you would infer less density. So you need to take that into account when you try to construct this bias into account, when you try to construct the underlying matter power spectrum. So that's one of the difficulties that you have to deal with. So bringing us up to the current status, more or less. So this is a power spectrum measured by the Sloan survey in one of its many, many incarnations. So what you see here is, as a function of wave number, actually a very precisely measured power spectrum. It's really quite astounding, right? That you can measure power to a few % precision. So that really does look very, very promising. And how do you then, for example, infer a neutrino mass from that? I think we'll end up with that. I'll be done in a minute, roughly. So qualitatively, let's just remind ourselves, what is it that neutrinos do that dark matter doesn't? Well, neutrinos move fast, and that means that they erase all structure in neutrinos basically out to the Hubble distance scale at the time where these neutrinos go non-relativistic. And that means if I have neutrino dark matter rather than cold dark matter, I would expect to see a different looking universe. And how extreme that is, we can see, hopefully. Let's hope that this works properly. Let's try and give it a minute. Okay, it's quite stubborn. Otherwise, download it yourself from Indico. And okay, yes, well, okay, if you look at this, they look quite identical. So download it yourself, and you'll see what actually happens. So if you have a universe with a quite large sum of neutrino masses, the reason I chose this for the simulation was that this corresponded to the limit on the neutrino mass prior to the Catherine experiment. So this is the limit that you got from direct detection experiments. And if you see these two seemingly identical blobs of red evolving forwards in time, then you would see that there's essentially no structure in this one, and there's a lot of structure in this one. Give it one final try. Ooh. Yes. Okay. I mean, even by naked eye, you can see these are radically different. They're different to an extent where this would be vastly excluded from observations. And we wouldn't even be here to worry about it because there would be no such thing as a Milky Way galaxy in this model. So clearly, cosmology can be used to probe neutrino physics to a precision in terms of the mass, for example, to a precision which is way better than this. And as we'll see tomorrow, actually the current bound on the sum even of neutrino masses is of order 0.1 electron volts now from cosmological data. Just the final slide for today, I think, should be this one. So this is a condensed form of the movie I just showed you. This is actually the power spectrum in a model with a neutrino mass compared to one where the neutrino mass is artificially set to 0. And here you see, and I have no idea why it can, okay, so this should be a capital sigma, not an S, but the sum of neutrino masses 0.3 eV and 1 eV. And what you can see is that if you had a sum of neutrino masses of 1 eV, you actually get a factor of 2 suppression in power. That's a very, very measurable quantity. Remember, we can measure the matter power spectrum to percent level precision, right? However, even though I showed you this figure that we can measure to percent level precision, that's not the same as saying that we, with current data, can actually measure the neutrino mass to 0.0 something electron volts, because the problem is that we don't only have neutrinos in the universe, we have all kinds of things, and there are many other types of physics that could lead to effects that look fairly similar to this. So unfortunately, it's not as simple as this figure would seem to indicate. But in order to well, get us started for tomorrow, what I can say is that, as probably many of you know, ESA's Euclid mission was launched roughly 2 weeks ago, 3 weeks almost now. And with the data from the Euclid satellite, we probably, at least that's what we've been running around, or I've been running around and claiming for the past 10 or 15 years, is that with that data, we will be able to measure the neutrino mass so precisely that we can actually make a non-zero, an actual detection of the neutrino mass, even if neutrinos are as light as possible if you take oscillation experiments. So hopefully within 5 years from now, we actually will know whether it's the normal hierarchy or the inverted hierarchy, for sure, also from cosmology. And more than that, we'll also know the exact value of the neutrino mass. So that's going to be quite nice, I would say. That's the final parameter, more or less, of the standard model that gets fixed by this. Okay, enough for today. Yes, questions?
Thank you, Steen. Sorry, I had to run out to catch a delivery.
Yes.
Other questions?
Yeah, do you think maybe you could elaborate a little bit more on how to like interpret the power spectrum? It's like, okay, sure, it has a peak at k equals 0.01 maybe. What does that mean for the universe and how that is?
Yes, I can. Okay, so why the hell does it look like this? If I start from, the claim was, I start from a power spectrum that's just a power law, right? So why does it end up having this totally weird shape? It's a very, very good question. So there are several effects. So what I talked about was mainly related to, if you want, causal evolution, in the sense that we looked at all these Newtonian equations. We looked at sound speeds and whatnot. I never really talked about the super horizon. What happens to a perturbation that sits outside the particle horizon? It's not subject to normal causal physics. On the other hand, every point in space feels a metric, and therefore a density surely can evolve and does evolve even when a Fourier mode is outside the horizon. That doesn't require interactions other than through the metric. Now, what happens is that when the universe expands, more and more stuff comes inside the particle horizon. So the particle horizon, or the Hubble horizon, or whatever you call it, grows roughly proportional to time. And in the radiation and matter-dominated phase of the universe, the scale factor grows slower than that. And that means that more and more of the universe becomes visible to us, and also, of course, to causal physics. So that means, remember, the power spectrum is a function of the wave number, and large wave number corresponds to small physical scale. and vice versa. So that means these scales come inside the particle horizon first. And then we shift in this direction. And if we reach something like 10 to the minus 5, that's where the Hubble horizon is today. That cannot be measured in large-scale structure surveys, but can be measured in the CMB. So everything here to the right of the peak is stuff that came inside the particle horizon prior to matter radiation equality. That means it has lived inside the horizon during the radiation-dominated phase where structures don't grow. But outside the horizon, structures do grow. And as it turns out, without going into details, that's exactly why there's a peak here. Everything to the right comes inside the horizon, more or less freezes up. And what is true is that in terms of real space perturbations, the amplitude is more or less the same for all scales. But if you convert that to Fourier space, you get a k-cubed factor, right? Because remember that when you do a Fourier integral, basically you have the Fourier volume that you have to multiply with. And that means that a scale invariant real space thing corresponds to a decreasing k-space thing. So that's maybe what confuses at least many people. You seem to have this 1 over k cubed dependence of the power spectrum. So why don't you have less structure over here and more structure over here? But that's not the case. This is just a Fourier spectrum and not a real space thing. In real space, the amount of fluctuation on a given length scale would be k cubed times p of k, which is more or less scale invariant. Okay, so the peak here corresponds to the Hubble scale at matter radiation equality. Everything outside is basically not subject to any kind of causal physics. Everything grows together, and that means you get exactly this k to the power 1 behavior over here. And then you stitch the two together, and that's what you get. And as we'll see tomorrow, I didn't have time to talk about it today. You see these small oscillations to the right of the peak. Those are what is called baryon acoustic oscillations. They're the same oscillations that you see in the CMB spectrum, but they are much smaller in amplitude because the matter power spectrum is dominated by the dark matter component that does not suffer from acoustic oscillations. And the baryons are only a subdominant component. Therefore, you get these small scale fluctuations. I don't know if that's...
Yeah, I think maybe my question was a little simpler than that.
Okay.
Or at least a little less involved. I'm just trying to find out, okay, I have a power spectrum. It's some function.
Yes.
I just want to know how to interpret that function. What does that specifically tell me? If I have a power spectrum that looks like this, what does that tell me about the universe?
Okay.
Because it's
but
Fourier inverse.
Once you know all the stuff that I just blabbered on about, then you can start to do the interpretation. So, for example, let's say I have a universe that has a higher radiation amount than in the standard model. I have some dark radiation or other stuff around. That means I delay matter radiation equality. If I delay matter radiation equality, what happens to the peak? It must move to the left, for example. If I have dark energy, what happens to this power spectrum? If I had more dark energy, then the matter-dominated phase of the universe does not last quite as long as it would have otherwise, right? And as soon as dark energy takes over, structure formation stops. So I would expect in such a universe to have a shifting overall of the total matter power spectrum. So the more dark energy I have, the less power I should have here. Of course, more dark energy also leads to, if I have a flat universe, it would lead to less dark matter, in which case I also move this stuff to the left. If I have neutrinos, well, you can sort of guess from what I showed you right at the end, that what would happen is I have more or less the same thing here, but then I have a dip. Then the question is, how do I separate that effect from changing the matter density, for example, or fiddling around with the baryons or any other type of stuff?
Okay, thank you.
I have a question regarding the galaxy redshift survey.
Yes.
The slide. Can you please show this?
Absolutely, yes.
Okay.
This one?
Yeah.
Yeah.
So my question is quite naive. Why is there no surveys done for like between 4 hours and 9 hours and at the bottom?
Yeah, it's a good question. I mean, typically what you're up against in these surveys is the amount of telescope time that you have available. I mean, they're super expensive to do in terms of telescope hours. It's not like observing a star or a galaxy, right? You have to observe the entire sky as deep as possible, which means that you have to spend as much time as possible with the telescope that you have available. And then you have to choose how do you best structure your survey. And one way of doing it is to make these like the 2DF survey, make these bands. So these are basically bands of 2-degree thickness on the sky. That's the name. And then you typically exclude the galactic plane and anything close to it because it's very hard to see through the galactic plane. And therefore you sort of stitch two cones or whatever you want to call them, slices together that are as orthogonal to the galactic plane as possible. Now, if you have more time available, such as with the Sloan survey, for example, you can thicken these. So the 2-degree field also became the 6-degree field in the end, but Sloan goes much further. And Euclid, for example, will measure something like 50% of the entire sky, which of course is radically more than this. But it's in the end, it's all down to the sensitivity of the telescope that you have and the amount of time that you have.
So the Milky Way galaxy lies at the center? Like,
that sits here. Yeah, so you think of the Milky Way as if the disk sits here, then you try to observe like in this direction, right? You find directions where the intervening material is as little as possible. That's basically the trick always, which means observing away from the disk. Yeah.
Thank you.
Questions?
Yeah, regarding the neutrinos are washing out large-scale structure formations.
Yes.
So intuitively, this does not make much sense for me because in the neutrinos, they don't interact. So why would matter care? And also they don't have much mass. So why would matter care? If I just have...
No, it's a very good question. Why does it even matter?
Yes.
And of course, the answer is that if we have the neutrino masses that we know we have, which are very much a fraction of an electron volt, it's not a dominant effect, right? It's more of a perturbative effect, but it's much stronger than you think. If you actually write out the equations, you find out that if you take neutrinos can be thought of basically as an unperturbed energy component, right? So it's just something that contributes to the expansion rate of the universe, but it doesn't cluster to a good approximation. Then you find that the effect that you get is actually about 8 times larger than what you would naively think. So naively, perhaps you would think that the suppression, maybe you would get something like this. Let's say that, I don't know if you can see it, but let's say the relative suppression of what should I call this? I should call it delta, you know, the density perturbation divided by, there's already a dimensionless quantity. Like this, sorry. Okay, so if you change, now I think we're getting there. So if you have neutrinos, you would think that the presence of neutrinos should lower delta roughly by a fraction corresponding to the relative density of neutrinos to matter.
Yes.
What you actually find in the end, surprisingly, is that there's approximately a numerical factor of 8 there, which means that large-scale structure is actually surprisingly sensitive, even though neutrinos make up very, very little. If you have a neutrino mass of, say, 0.1 electron volt, I mean, it makes up something like, what, a per mil or something, a little more than a per mil. Let's say a few per mil of the density of the total matter density. Yet it contributes an observable distortion to the matter power spectrum. And it's actually not super difficult to derive this factor of 8. So if you're interested, there's a very nice but also very lengthy review by Sergio Pastor and Julien Lescourge on neutrino cosmology. It's close to 20 years old by now, but there in great detail they derived this factor of 8. It's also what you get numerically, but they have a very nice like analytic derivation of why it's 8.
Okay, thank you.
Okay, then we should break for coffee now. We also have this question Q&A session in the evening after
Yes.
the exercises. And yeah, speaking of the exercises, I just passed around the exercises for today, which will be focused on human cosmology or cosmology in general. So with that, let's have another round of applause for